Okay, so this is problem 2.34 out of Griffith's quantum mechanics. We have a potential step. So we have something that looks like this. No potential. And then we have this potential here at a level V naught. This is at x equals 0 where that happens. And it asks us to do a whole bunch of stuff. So we're going to go through that. But before I start this, if you wouldn't mind please liking the video and subscribing, I'd really appreciate it as I'm trying to build my channel a little bit. Okay, so let's start with A. It wants us to calculate the reflection coefficient for the case E is less than V naught. Comment on the answer. So E, the energy, is less than this potential step. So let's start with x less than or equal to 0. Okay, well, we can start with just Schrodinger's equation. Minus h bar squared over 2m, the second derivative of psi with respect to x, plus v times psi equals e times psi. But remember that the potential is 0 in this case because we're over here in region 1. So this is just 0. So we could rewrite this as the second derivative of psi with respect to x is equal to minus e times 2m over h bar squared psi. Or we could write this as the second derivative of psi with respect to x is equal to minus k1 psi, k1 squared psi, where k1 is 2m times e square root divided by h bar squared. Okay, and the solution for this differential equation is psi of x equals a e to the I k1x plus b e to the minus I k1x. And just to talk about this a little bit, this is essentially what you get with a free particle. So this is just like the free particle section of the book. And what you get because of Euler's identity is this is oscillating waves. It's just moving right around. So in this first region, our wave function is going to happily wiggle around, however it's wiggling. But then it's going to hit here at x equals 0 and everything beyond that. So now we want to say, well, what happens when x is greater than 0? Now classically, if your energy level, let's say it's here, is less than that potential step, then you wouldn't even have the particle over here in this second area. A good analogy to think of is, it's kind of like if you were at this little, let's see if I can make like a hill, and you have a ball right here that you're going to drop. The energy you're giving it through the potential energy only has so much. It's not going to go above that little dashed line. It's not going to jump over here and get past that potential step. However, in quantum mechanics, you do have tunneling effects to consider. So now it's going to be very similar. We're going to have the second derivative of psi with respect to x plus, well, let's do this. Let's just write it all out. minus h bar squared over 2m, the second derivative of psi with respect to x, plus v naught psi equals e times psi. And we can, rearrange this differential equation a little bit. It should be squared. Okay. Just doing a little bit of algebra. And then we can replace a lot of those values with just this fancy looking kappa. The book uses kappa a lot, so I'm trying to be consistent with it. And kappa, kind of a clown move by Griffith to use k's and kappas together, but it's okay. It's still a great book. So kappa is equal to that. And then psi of x is f e to the minus kappa x plus d e to the positive kappa x. And it's important to know because you might be like, well, why is this any different than this? And the main thing is you're no longer going to have, or the way that I like to think of it intuitively, is this red line, I'm going to draw it in blue now, isn't going to wiggle because it's tunneling through this potential. It's decaying. So your wave function is going to look more like this, making the probability of finding it less and less the further down x you get. So now we're not getting this oscillating wave, we're getting a decay wave. And if we normalize this, we can see d has to be equal to 0. And that's just because if you were to take the limit of psi of x as it approached infinity, well, you're going to have a little bit of an issue because now our wave function is not normalizable. And we don't want those solutions, so we just make that that way. So, handy little rule of thumb is, in situations like this, if your energy is greater than your potential energy, you're going to get wiggle physics. My waves aren't very good, but you're going to get something like a e to the ikx plus b e to the minus ikx. But if the energy is less than the potential, now you have tunneling. You're in a classically forbidden region. So you would get something like c e to the kappa x plus d e to the minus kappa x. So that's just kind of a helpful way to go through that. Anyways, after you're good with that, you want to apply boundary conditions. So psi at 0 from the left should equal psi of 0 at the right, from the right. So you can plug these values in. They're 0, so they're really easy. But you're essentially going to get a plus b equals f. That's what this gives you. Then there's another boundary condition which tells us that the first derivative of psi at 0 from the left should equal the derivative of psi at 0 from the right. So once again, these aren't too hard to take a derivative of. You'll get an ik1 and a minus ik1 out here, and just a minus kappa from right there. So if you apply these, you'll get ik1 a minus b equals minus kappa f. Okay? So do a bunch of different things here. One thing you could say is, well, f is a plus b, so I'll just replace that with a plus b. So then if we do that, you get ik1a minus ik1b equals minus kappa a minus kappa b. From there, we can work towards isolating a and b. So I k1a plus kappa a equals I k1b minus kappa b. Okay, so we can see that b then is equal to I k1 plus kappa all over I k1 minus kappa times a. So then we can find that b over a is just this term right here. Okay? So we can find that, and the problem wanted to find just the reflection coefficient. So we should be okay with just that. Okay. So let's see, this would be equal to I k1 plus kappa over I k1 minus kappa times the complex conjugate, so minus I k1 plus kappa over minus I k1 minus kappa. And you could go ahead and distribute this. Negative I squared is 1, so that's going to be k1 squared. Let's see, plus ki minus ki, so plus kappa squared all over k1 squared plus kappa squared, or 1. So this is your reflection coefficient, and what it's saying is basically the entire wave is being reflected. Okay. Part B says to calculate the reflection coefficient when E is greater than 0. Okay. Let me adjust that a little bit. So basically have the same wave functions we had before. That doesn't change. I think we did that for this case, right? So let's see. E greater than V naught, x less than or equal to 0. So the first wave function will stay the same because that doesn't change anything. But what does change is when we look at x greater than 0, it's going to be set up the same way, where psi of x equals fe to the I, we'll call it k2x instead of kappa. The only difference is we're not decaying anymore. So if we look back at this little picture, our energy is now like up here. So it's enough to overcome this potential step. So now we're no longer going to get any sort of decay. We're going to get some wiggling stuff going on. So that slightly changes your boundary conditions. The first boundary condition should not change at all. This tells us a plus b equals f. But now, when we take the derivative, it's going to be slightly different. So we're going to have I k1a minus I k1b equals I k2f. And we have to solve for these coefficients. Kind of can do it the same way basically if you wanted. You have f is equal to a plus b. You could substitute that in and then find your reflection coefficient. You essentially just want to manipulate this equation until you find b over a, and then you take the complex conjugate the complex conjugate time, or the wave function, or your b over a times the complex conjugate of it. So that's all you're doing there. I'm going to just leave that because that's pretty straightforward once again. So that's B. For C, some of this is just algebra, I'll kind of leave it. For C, just to kind of help you guys out, it mentions V quantum is E over 2m square root. So then your transmission coefficient is the intensity of these guys, the transmitted versus incident, which is F over A times V transmitted versus V incident. And essentially what you're doing is you're saying that that is equal to your Vt over Vi, this velocity. And in this case, it would actually be your effective energy, which is E naught, E minus V naught. And then you can substitute that into here. I think one part just has you add them and make sure that they equal 1. So conservation of energy. It's mostly just manipulating your equations and adding them. If it's something people really want to see, I'll do that. But I think really most of the physics was what we did here. So hopefully that helps, and if it did, please like and subscribe.